Lecture 5, A Tale of Three Planets, with apologies to Charles Dickens, I suppose. We've seen evidence that Earth's climate is changing. Then in the most recent lecture, we saw the theory of what establishes a planet's climate, that theory involving the basic idea of energy balance, that the energy that arrives from the planet's star, in the case of our planet, and in fact our neighboring planets that I'll be discussing in this lecture, energy arriving from the sun, that energy heats up the planet, and the planet sheds the energy back to space as infrared radiation. And regardless of whatever else goes on, we know that if the sunlight is shining steadily and the conditions of the planet are steady, the planet will come to an energy balance at a constant temperature, and that temperature will be maintained essentially unchanged as long as none of the conditions, the incoming sunlight or the ability of the planet to shed that energy back to space, change. On the other hand, if any of those conditions change, the planet will come to a new energy balance at perhaps a new temperature. So we've seen Earth's climate changing. We've come to an understanding of how climate arises in planets, but I've given you basically there a theoretical understanding. How do we know that that's correct? How do we know that this theory that energy balance establishes a planetary climate, and particularly the idea, the theory of the greenhouse effect, the idea that there are gases in the atmosphere of a planet, particularly of Earth, that are opaque to outgoing infrared radiation, and therefore they require a surface temperature that's warmer than it would be in the absence of those gases? How do we know these theories are true? One of the nice things scientists like to do is experiment with nature. They like to do controlled experiments. They say, let's set up this condition, and let's put more greenhouse gases in the atmosphere, and let's see what happens to climate. And they do carefully controlled experiments. Well, unfortunately, Earth's climate is one area where you can't easily do carefully controlled experiments. You can't play with the climate. You can't decide, we're going to double the amount of greenhouse gases in the atmosphere, we're going to see what happens, we're going to decide if we like what happens, and then we're going to undo the experiment. We can't do that. We don't have multiple Earths to work with to perform different experiments on. It would take a long time for climate to change, even if we could do experiments. It's difficult to establish miniature climate experiments. It's impossible to put a tiny Earth in a laboratory and do realistic climate experiments. Now, having said all that, that doesn't mean there aren't some things we can know experimentally. For example, we can put carbon dioxide in a chamber, we can send infrared radiation through it, we can measure how much of the infrared radiation gets through, and consequently we can determine the opacity, that is, how much the carbon dioxide blocks infrared radiation. So we can then determine, if we put so much carbon dioxide in the atmosphere, how much infrared radiation will it block. That's something we can measure experimentally, for example. As I'll describe in a subsequent lecture, we can also build, if you will, simulated climate systems, Earths and atmospheres and oceans and suns and all the rest, and put them in computer models whose mathematical programming represents the physical and biological and chemical science going into these systems, and we can run these models and try to understand how climate would behave under other circumstances. And climate scientists who do that actually call these computer runs experiments. But they aren't experiments in the sense of our grabbing onto nature itself and doing things and trying to figure out what happens. We can't do controlled experiments with Earth's climate, unfortunately. On the other hand, there are many who would argue we are in fact doing inadvertent experiments on Earth's climate by, in fact, altering the amount of greenhouse gases in the planet's atmosphere. But those aren't controlled experiments. Those aren't experiments we are intentionally doing, and they aren't experiments where we're controlling exactly the effect we're producing. So we can't do experiments to verify the theory of the greenhouse effect that I described for you in the last lecture. So how do we know it's correct? Well, I'm going to give you in this lecture several arguments why we are quite certain that the greenhouse effect is a serious and important explanation of what is happening to our planet's climate, what establishes the climate originally, and what's happening now as the climate is changing. One argument I would give you is that the basic physics I described in the previous lecture, the physics that goes into the greenhouse effect, the absorption of infrared radiation by carbon dioxide, the presence of carbon dioxide and water vapor, both absorbing infrared radiation in the atmosphere, these are things we can get in the laboratory. We know, for example, that law that I referred to last time about the amount of infrared radiation depending on the fourth power of the temperature. That's something we can verify in the laboratory. In other words, that whole theory of the greenhouse effect that I described to you in the last lecture is something that's based in very sound, basic scientific principles that we know from theory and we know from measurement to be true. It's not some cooked up theory designed to explain one particular thing, namely Earth's climate. It's a theory based on very fundamental, very sound, very long established scientific principles. So there's one reason why the theory I described for you last time, and I'm using that word theory intentionally, and at the end of this lecture I'm going to talk a little bit about what scientists mean specifically when they say a theory. So one reason we believe the greenhouse effect theory to be correct is because it's based in very sound and very fundamental science. What's another way? Well, in my arguments last time, I suggested that the presence of the greenhouse effect, the 33 degrees Celsius warming that the Earth experiences relative to what it would have if there were no greenhouse gases in the atmosphere, that's caused by the presence of water vapor and carbon dioxide in the atmosphere. And so perhaps if we looked at the atmospheric carbon dioxide content and the atmospheric water vapor content over time, and we looked at Earth's temperature over time, and we saw a correlation, we might be able to argue that, in fact, the presence of one infers the climate change associated with the other, for example. Now, I'm going to try to do that in the first part of this lecture, but I want to warn you at first that this is a little bit more subtle than a very quick glimpse at the data might suggest. First of all, water vapor, I argued last time, is the predominant greenhouse gas in the Earth's atmosphere in terms of the natural greenhouse effect. That's true. People tend to forget that. When they hear greenhouse effect, they tend to think carbon dioxide. But in fact, the natural greenhouse effect is dominated by water vapor. Carbon dioxide is important, it's significant, but it's not the dominant greenhouse gas. The carbon dioxide, though, plays a much greater role in regulating the strength of the greenhouse gases and the strength of the greenhouse effect. The reason water vapor is less important in that regard is because water vapor adjusts itself in the atmosphere almost instantaneously to the conditions in the atmosphere. If the atmosphere were to warm, for example, causing more evaporation and therefore more water in the atmosphere, that effect would be felt almost immediately. The time scales associated with changes in the water content of the atmosphere are on the order of a week. What happens to the water? It evaporates, gets into the atmosphere. Within about a week, it precipitates back out and lands on the surface. And so the water vapor content of the atmosphere adjusts very, very quickly to changing climatic conditions. Not so carbon dioxide, particularly not so carbon dioxide. And I'm going to present you some reasons in the next lecture about precisely why that is and have you come to an understanding of why carbon dioxide is so unique. But for the present, the important point is this. Changes in the carbon dioxide content of the atmosphere are most significant in causing changes in climate, we think. And I'm going to show you why precisely we think that. So although water vapor is the most important natural greenhouse gas, carbon dioxide plays a much bigger role in regulating climate. So what we'd like to know about is what the carbon dioxide content of the atmosphere has looked like over time. And how are we going to measure that? Well, if we want to go substantially far back in time, those very same ice cores that gave us these isotopic temperature measurements, the measurements of temperature based on the ratio of oxygen or hydrogen isotopes, the heavier isotopes being more slow to evaporate and more soon to precipitate out, and that giving us an indication of temperature at the time the precipitation fell that has now become ice. We can more easily measure the carbon dioxide content of the atmosphere at that same time because trapped in that ice are small air bubbles. And they contain, if you will, fossil air from the time that ice was formed. Now, there are some subtleties here, as always in science. For example, that air diffuses somewhat through the ice, and there are corrections that have to be applied for that. And scientists know about these corrections, and they believe they're applying them correctly. So if you want to get precise dating of the carbon dioxide bubbles, you have to apply a little bit of a correction. We know about that. We understand that. And when we do that, we can get a record of past atmospheric composition, in particular, past carbon dioxide levels. And how do we measure that? Well, we measure it in concentration, typically in a measure called parts per million, ppm, sometimes for even rarer gases in parts per billion. Strictly speaking, you have to specify something more besides saying parts per million or parts per billion, and you say parts per million by volume or parts per million by weight or whatever. And when we're talking about atmospheric gases, it's essentially always parts per million by volume, which you will sometimes see abbreviated ppmv. And if you want to, or just ppm, if you want to picture what that means is, imagine a milk jug, a 1-gallon milk jug, and imagine you took 1 million of those and you filled them up with air. And if you had done this in 1750, before the Industrial Revolution started and before humankind started burning fossil fuels in abundance, you would have found that out of those million milk jugs, each a gallon in size, each containing air, if you had separated out the atmospheric constituents, in the pre-industrial era, about 280 of those milk jugs would have contained carbon dioxide. That's what it means when I say the pre-industrial concentration of carbon dioxide was about 280 parts per million. I mean, of all the volume in the air, by volume, about 280 gallons out of every million gallons was carbon dioxide. That number's changed, and we'll talk about that change in number subsequently in the lectures where I talk about the human influence on climate. But until humankind began putting a lot of carbon dioxide in the atmosphere, the amount we had, the concentration, was about 280 parts per million, ppm, and that's what that means. So what we would like to do now is consider those same ice cores that I showed you data from earlier, and I showed you at that point only temperature, and we're going to look now at both temperature and carbon dioxide.